On behalf of Engineers Australia, I'm delighted to welcome you all to today's webinar, Seismic Resilience in Bridge Design. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past and present. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Magiba Australia. Magiba Australia is a local division of the globally recognised civil engineering company, Magiba, which has been engineering connections since 1963. The company is a leading provider of high-end structural bearings, expansion joints, seismic protection and structural health monitoring systems for bridges, buildings and industrial structures. Now, today's webinar will feature two speakers followed by our live audience Q&A, so I encourage you all to please send your questions through to our speakers via the chat box. I now have the pleasure to welcome our first speaker, Masood Homasood, Head of Engineering at Magiba Australia. Masood is a distinguished researcher and structural engineer from the University of Auckland's Department of Civil Environmental Engineering. Masood is at the forefront of developing next-generation seismic isolation technologies with a specialised focus on enhancing the safety and resilience of critical infrastructure. His research delves deep into the performance of lead rubber bearings, a cornerstone of modern seismic design. His extensive hands-on work is validated by the analysis of over 350 tests and full-scale bearings, leading to practical and impactful refinements for the engineering industry. As an active contributor to the engineering community, Masood regularly presents to his peers at the New Zealand Society for Earthquake Engineering conferences, and he brings a wealth of specialised research-driven knowledge and offers invaluable insights into the future of seismic protection for modern bridges. Please join me in welcoming Masood Homasood.
Hi, thank you very much for your introduction. I'm very excited to be here talking about seismic resiliency for buildings and bridges by seismic isolation system. Today, we're going to talk about introduction of seismic isolation, and after that present a full scale shaking table test and follow that up by a real world experiences for this kind of buildings. And then we're going to talk about how seismic isolators work and what's the principle of them. And just briefly talk about seismicity of Australia and if base isolation is something required for this region or not. And then we're gonna talk about lead rubber bearings as one of the systems that's known as base isolation system, and then explain how to model seismic isolators in engineering softwares. The concept of base isolation comes from decoupling any kind of structure from ground motion. So the idea is that while ground motion is happening, the superstructure going to behave separately and filter any kind of force or acceleration from being imparted to the superstructure. Over here, I've got two quite simple physical model that's going to illustrate how the base isolators work. On the left-hand side, you can see the performance of a fixed base structure during earthquake. The point is that even if the structure itself going to remain intact and sound, the non-structural elements like decoration, light, or piping, which are quite sensitive to acceleration, going to be damaged severely. On the right-hand side, you can see the concept of using base isolation. As you can see by movement of that box, the content going to remain kind of intact with minimum vibration actually, and they're not going to end up to any level of damage. And if you compare those waters inside and outside of the box, you can see that on the outside, the splashing of water is obvious. So this one is testing a full-scale test that has carried out many years ago, actually, but it's quite interesting for engineers to see how a real project gonna work. The first one starts with a fixed space option.
9, 8, 7, 6, 5, 4, 3, 2, 1, running.
The violence and severity of the quake is clear. This would be a frightening experience not soon forgotten. The forces and displacements on the structure are extreme. At points during the shaking, floors 2 and 3 are displaced by nearly a foot in both directions. The heavy upper cladding is shaken violently, but remains attached. The lower cladding tears like paper. Interior furnishings are thrown about by the violent accelerations. Those that are unrestrained are tossed about like toys, while anchored items ride out the seismic storm, jerked to and fro, along with the walls and floors to which they are attached. Close inspection reveals that the building suffers irreparable damage.
I think this building in a real world situation would be condemned. The columns, the base of the columns, the concrete is falling off, especially the 2 columns on the east. There is a beam at the top of the first story where there is a full plastic hinge formation with a lot of concrete that detached. You see these blocks of concrete here. We can see the rebars. They are naked now. At different floors, you can see the formation of the punching failure mechanism of the slab around the column, not far from really collapsing. From the 3rd floor to the 4th floor, the stairs are detached. They are hanging. There are a lot of gypsum board, huge gypsum board that detached, that fell off.
The building didn't collapse, however, it was prone to collapse actually. But before this test, the fixed space option was tested firstly because the researchers knew that it's not going to end up to any level of damage. So they first of all tested the base isolated one, and after that went for the fixed space one. And here we are, we're gonna go for the base isolated option.
Prior to conducting these ultimately damaging tests, the team had tested the building on seismic isolators in order to directly compare the effects of seismic isolation on the performance of non-structural elements. These huge rubber pads, each weighing over half a ton, support the building on 4 points, one at each corner of the structure, isolating the building from the earth and its motions. In a test using a record from the magnitude 8 Ica, Peru earthquake of 2007, the effect of base isolation becomes obvious. As the table displaces, the isolators provide elastic joints between the earth and the structure, dramatically attenuating the accelerations that are transmitted to the building. The contrast with the motions in the other tests is clear. With isolators, the building slides back and forth smoothly and easily. While objects and fixtures shift, the violent displacements and the destruction they wrought upon the building in the fixed foundation tests do not occur.
90% or so of the displacement that actually was imparted on the building was absorbed by the isolator. And so the result is relatively minimal impact on the contents and the non-structural elements in the building. The hospital could remain functioning. The patients would be safe. The equipment, critical support equipment would remain functioning. The electrical system in this building remained functioning. So life support equipment for patients would remain functioning. That's essential. The elevator remained functioning. The stairs were completely intact. So paths of egress through the building remained functional.
As you saw, for the fixed base option, most of non-structural elements tossed around and damaged severely. However, for the base isolated one, all elements, including structural elements as well as non-structural elements, moved around quite gently. So the next question is that how it's going to happen in reality. To explain this question, I'm going to refer to a couple of earthquakes. And the first one is what happened in China in 2013, actually. It was an earthquake that was not necessarily in a seismic region. And the design acceleration for that region was predicted something about 0.15 G, while what happened was considerably more than that, something about 3 to 4 times more, actually, that ended up to plenty of collapse and damage, particularly to concrete buildings. In that city, there was a hospital campus. 2 buildings was without isolation, and 1 building was base isolated. As you can see over here, it was explained on the report of the project that the isolation hospital building became the unique rescue center in whole country after earthquake, and thousands of injured people accepted first aid rescue in this project, actually. So no damage happened for this project, and all of medical equipment remained functional and intact. You can compare the top photos for the fixed base one after the earthquake and the base isolated one, which is again after earthquake. Another example that I would like to refer to comes from 2023 Turkey earthquake. And as you probably have heard about that earthquake, there was 2 main fault line. On the right hand side, you can see that on the bottom one, there is a fault line, and most of fixed base building, now the F over here, letter F, represent fixed base hospitals, was aligned with this fault line. And the second one was an earthquake magnitude 7.5, and the base isolated hospitals was quite close to this one. And there was 2 specification for that earthquake. The first one was that we've got again another hospital campus. One of the buildings was fixed base one, and another one was base isolated one. And so we could compare the performance of these 2 hospitals together. And the second one was a hospital called as Hatay Education Hospital. It was a almost new brand. It was completed 2013, and it was just 10 years old. And it has got more than 1,000 hospital bed in this project. So these are very interesting photos that got kind of viral after the event, actually. On the left-hand side, you can see 2 photos. This photo is showing the hospital on the background, which sounds apparently kind of sound and safe. However, due to non-structural elements and damage to the facade, they needed to evacuate that, and that hospital replaced with some tent. And on the bottom one, you can see that the hospital beds have been replaced with just some tent, and the doctors, nurses have been replaced with some rescue workers from international help, actually. And on the right hand side, you can see the level of damage to the facade. And over here, you can see that some yielding has happened for the bars, actually, and all of the facade on this photo have been damaged. So it made the project non-functional. And the same scenario happened for another project over there. For this project, the acceleration was not necessarily quite high. However, you can see the level of damage to non-structural elements, particularly for example, on the bottom right-hand side, you can see that it has been a surgery room that is not functional in any shape after earthquake. So I already mentioned there was a campus with fixed base one and base isolated one. You can see here this project was fixed base one, and what we got on the background is base isolated one. On the right hand side over here, you can see the acceleration that that imparted to the superstructure actually, and it was sort of low, something about 0.16 acceleration is quite low number. However, it ended up to some damage for the fixed base project. As you can see over here on the report, for B1, the non-structural damage was quite slight, and was present only in the surrounding, the isolation level, because normally isolators got some cover around them. So during the movement of earthquakes, some of those covers might be damaged as well. However, the superstructure remained functional after earthquake and it worked as normal. On the other hand, the fixed base hospital ended up to again some damage, particularly for non-structural elements. And the interesting point for this report was that it has written over here that the manager of the hospital said that they sent workers to repair the damaged non-structural elements after the earthquake. But during an aftershock, the workers in the building were scared by the violent shaking of the building to fled from the building and refused to enter the building anymore. The recovery of the building seemed impossible in the near future. So this is about the downtime that we normally faced after earthquake, and it ended up to avoiding the project to be used for probably at least months or maybe years. And another example that I'm going to go through shortly is about the performance of bridges during 2010 Chile earthquake. It was a sort of quite a strong earthquake that was followed by tsunami as well, and ended up to a lot of casualties, unfortunately, as well. During this earthquake, many damage to buildings and infrastructures happened, and about 25 bridges was collapsed. However, fortunately, seismic isolated bridges survive. In this slide, you can see a number of bridges. All of these photos are taken after earthquake, and fortunately, all of them remain functional and intact. So if I'm gonna to zoom on one of these projects, I'm gonna go for Marga Bridge, which was seismic isolated and also equipped to health monitoring system as well. On the right-hand side, you can see that the height of piers was something between 22 to 32 meter. And this project, as I already mentioned, was equipped to some sensors that you can see on the top photo on the right-hand side. These are the records that has taken after the earthquake. You can see that on both sides of bridge, there is two sensors. Sensor 11 on the left hand side, which is located on the ground, on the abutment actually, and on the right hand side we got sensors 70. The level of acceleration that was recorded by these sensors was something about 1.9 and 1.4. However, on the deck, the acceleration considerably decreased, and as you can see over here, it has ranged from 0.6 to 0.3. And as you can see, a deduction of acceleration by half was happened by base isolation system, which shows how influential the isolators have been in terms of decreasing the acceleration. So, how seismic isolators work and what happened that it minimized the damage. The point is that by using base isolation, we increase the period of structure. For buildings, we normally consider a period of 3 times of period of a fixed base building. And this is almost similar for the bridges as well. Bridges definitely are softer than a fixed base building. However, we still increase the period of base isolated one to probably at least 2 times of period of a fixed base bridge. And also we increase the damping. So the damping gonna be increased from 5% to at least 20%. So as you can see, by increasing the period and increasing the damping, the demand and acceleration on the superstructure in terms of the buildings and substructure for the bridge is going to considerably decrease. So, for example, for a building that has a fundamental period about 0.05 second or 0.1 second, the acceleration that imparted to the building would be something about 0.6 g at least. So it's going to be amplified along with the height, and the floor acceleration probably on the top floor of a 5-story building gonna at least reach to something about 1.5 g, which means medium to extensive level of non-structural damage. However, by using seismic isolators, the period gonna be decreased to at least something about 2 seconds. And the acceleration on the isolation level gonna be probably attenuated by 80%. So ideally, we consider the superstructure acceleration something about 0.3 g to make sure that it's not going to end up to any level of damage. So the point is that there are some main differences in terms of using isolation for buildings and bridges. For bridges, the weight of superstructure is concentrated in a single horizontal plane on the isolation level. However, for buildings, it has distributed aligned with the height as a multi-story building. Again, for the bridge, the superstructure is robust in terms of resistance to seismic loads, but the substructure, piers, and abutment are vulnerable. So the most important point is that we use base isolators for buildings to keep superstructure safe during earthquake. However, for the bridges, we are using isolators to decrease the demand on the substructure. This is the most important difference of using isolators for buildings and bridges. If you are designing bridges, and particularly for seismic action, I highly recommend to go through this document, which is Seismic Performance of Isolated Bridges under Beyond Design Basic Shaking. It has covered very important data, and it gives us a kind of rule of thumb in terms of when isolation is required for the bridges. Over here, I have written that if the bridge has stiffer piers with a high natural frequency, the base isolation is highly recommended. This is based on this code. And also, if the shape of bridge is non-regular, again, the isolation is highly recommended. And the expected ground motion has a dominant high frequency content. In addition to these tips, this guideline talks about the experience of US in terms of using base isolated bridges. Over here, this guideline is talking about a bridge near to San Francisco that was firstly built in 1950, and after a few years, it was retrofitted in 1985. And during the Loma Prieta earthquake that happened 1989, no damage nor visible signs of distress were observed, which is quite important. And also it mentions that in the past earthquake in the US, however, there was reported damage to conventional bridges, definitely without isolation. Also in Japan during the 1995 Kobe earthquake, 6 isolated bridges suffered no damage, while conventional bridges nearly had major structural damage. So you can understand the difference of performance when you are using base isolation system. There are some key limitations of building codes that engineers are facing. The most important one is that we design any kind of structure, regardless of if it's a building or it's a bridges or whatever. Uh, Basic codes recommend ductility, and ductility means damage actually. Another important thing is that we normally design the fixed base or conventional project for just a single earthquake. However, the point is that major earthquake used to be followed with some strong aftershocks, which going to end up to some damage as well. This is a very nice diagram proposed with this code actually, and this is showing that how a base isolator is compared with building design and built by basic code. Over here, you can see that after earthquake for a base isolated structure, there is no downtime. So it means that the building going to remain functional. You don't need to waste any time fixing the elements or whatever. However, for the fixed base one, you at least will need fix months or even years to fix your buildings. Again, for the base isolated buildings, you probably going to spend a little bit more for the isolation level of isolation system. However, during the repair cost, any kind of pricing or costing would be minimized. On the other side, you probably gonna save by not using base isolation for your project. However, after earthquake, you will need to spend huge amount of money to can refix your project. So the main important question is that if Australia seismic and if base isolation system is something necessary for Australia, what we do need to consider is that we've got some records of sort of strong, medium, not necessarily strong. We can say that it has been kind of medium actually, because most of them have been less than or around magnitude 6. However, strong enough to end up to some damage actually. You can see the list of earthquake that has happened in Australia. The most important one has been Newcastle, that was 5.6, and another one was Adelaide. Again, this one was a 5.6. On the bottom, on the left hand side, you can see a piece of paper from 1954 that shows that quake hits many homes actually, and has ended up to terrified people running around this street as well. And again, on the right hand side, you can see some photos from this earthquake as well, showing the level of damage. So Australia Code 1170 published, I think, in 2021. And this diagram on the left-hand side is showing the epicenter of a known earthquake. As you can see, some medium to a strong earthquake has happened across the country. And over here, particularly on the south, you can see some magnitude 6 to 7 earthquake event has happened as well. This one is from 2021. However, 2022, another report was published showing that apparently Adelaide is high seismic zone as well. And there is a call from one of those researchers saying that we calculate that the 55-kilometer active length of this fault could potentially host an earthquake as large as magnitude 7.2. There is two main active faults under Adelaide, and one of them is right under CBD actually. And over here is written that if this earthquake happen, it's going to be 30 times more than what happened during New Zealand earthquake. That's going to end up to huge damage as well. So I shortly going to go through base isolator system and explain about LRB or lead rubber bearings, which is one of the most well-known isolators recently. LRBs are formed by rubber layers plus some steel shim plates in the middle of them, and a lead core in the middle, or probably multi-lead cores as well. What steel shim plates do is to minimizing the vertical deflection. If you just consider a rubber block, the vertical deformation going to be high. However, by using shim plates, we can decrease the vertical deformation. However, it's not going to affect the lateral movement or lateral flexibility. What lead core does is to providing damping. For a natural rubber bearings, without the lead core, you're going to end up to a hysteresis loop like that. By using lead core, you can provide up to 25% of damping, and your hysteresis loop is going to be fatter as well, which is going to end up minimizing the movement. I think due to time, I do need to go a little bit faster. So designing base isolators is a kind of iterative procedure. We start with selecting the size of bearing, making some guess in terms of the size. And after that, we calculate effective stiffness and damping. And based on this data, we can draw up the hysteresis loop of the isolators. And by having that, we can calculate the period and the required displacement, and it would be followed by the base shear coefficient. And this is the number that we need to calculate and design the superstructure. This kind of data will be passed to the consultant or structural engineer to be considered during the designing. Before I hand over my presentation to my colleague Virendra, I'm going to show you a piece of movie which is quite familiar for you. This is one of those Australian Lego masters that is about making a bridge and testing on the shaking table test.
You guys, I feel like, started with an aesthetic plan and then just rapidly abandoned it to get a bridge made.
You can see where the panic set in.
It's like a beautiful graph of confident, 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 panic.
I think objectively ours is the worst looking bridge in the room. But the only thing we have going is it's got a lot of bricks.
It's a very heavy boy.
Hopefully that weight of the heavy boy can really fight against the machine.
Yeah.
Brickman, the pillars are great. The top is great.
We just couldn't figure out the mounting mechanism.
And so far, they've been the weak points in all of
Yeah.
our bridges. So we'll see how we go here.
All right, you guys are on 4 wins in a row. You've held the titanium brick of triumph for a long time. You win here, the liquid titanium streak continues. Let's see how this heavy boy goes.
Level 2?
Yeah. All right, number 1, here we go.
I'm sorry.
It's a heavy boy. I feel like it's handling number 1, taking it to level 2. Oh. Heavy boy's starting, a little bit of creaking. Heavy boy's shoes are falling off. Heading to 3. Got to do some time at 3. I think this is where Heavy Boy might. Unsettled.
He's holding.
Come on, Heavy Boy.
Come on,
you can
Heavy
do
Boy.
it. You can do it. There's a lot of creaking, but it stays up.
All right, let's go level 4.
Come on, for all the heavy boys.
Do it for the big boys. All right, it's loose, but it's on. Level 5.
Actually, that's not working. It's like separated.
It's totally like floating.
Level 6. It's too heavy to move.
It's not going anywhere.
The bridge is just kind of hovering above the second pillar.
Level 7.
It is just, it's like surfing.
It's just not going anywhere, is it? All right, taking it to level 8.
This movie exactly shows the concept of base isolation for bridges. No one expected that this bridge going to tolerate, and it was kind of floated, but it means that it was actually base isolated. That was the main reason that this heavy boy didn't collapse. Thank you very much for your attention and your time, and I'm going to hand over the presentation to my colleague, Brandra. Thank you.
Thank you, Mr. for your input. I'd now like to welcome our second speaker, Brandra Gunke, CEO of Magiva Australia. Brandra is a pivotal figure who is reshaping Australian bridge engineering by championing a fundamental shift from short-term cost to long-term resilience and whole-of-life value. As the General Manager and CEO of Magiva Australia, Brandra has a tireless advocate against the false economy of specifying low-quality components, arguing that true value lies in custom-engineered solutions that ensure the safety and longevity of critical infrastructure. Brandra has twice been the driving force behind significant improvements to the Australian Bridge Design Code, AS 5100, successfully convincing the committee to adopt more rigorous performance-based requirements for critical components like structural bearings. He has helped institutionalise a new benchmark for resilience that will benefit Australian infrastructure for generations to come. Please join me in welcoming Brandra Gunke.
Thank you very much for the introduction and also for the first half of the presentation. I'm honored to take this presentation further and assist the engineering fraternity in general to incorporate the seismic resilience into the modern age designs. With Mageba Group, why Mageba Group would be a trusted partner for the structural engineers and bridge engineers across Australia and New Zealand, and for that matter, all across the globe. Let's start it with watching this video here. Thank you for watching the video. Why test facilities and testing is important is it's one thing to design a structure or a product or a solution for certain performance requirements. However, it's also critically important that we would be able to test and verify that design before implementing into the actual structure. It's quite prudent these days to challenge the norms or the status quo in the design, but also it's quite equally important to test them before implementing into the actual structure to avoid any shortcomings and identify any risks into that design which might have been overlooked. Again, why Mageba Group? We test all of our products and we present the data in terms of test reports, graphs, and the raw data where possible to the structural designers so that they can incorporate those numbers into their structural models and ensure their model does actually behave as intended. Mageba Group has a in-house design facility, including Mageba Australia. So we have over 4 experienced bearing designers, including the seismic and structural engineers, with cumulative experience of well over 80 years in designing bearings to Australian and global standards. We are state-of-the-art SolidWorks platform for designing and modeling the bearings and expansion joints, and we are supported by tens of more designers across 20 plus Mageba companies globally, if and when required. Most of our design team are active members of Standards Australia, or for that matter, the international code committees, which also provides more background as to the code requirements, and if required, more explanation onto why certain code requirements are there. Local design team is a big asset for Mageba Australia, and we would like to extend that facility to the Australia, New Zealand structural and seismic engineers to assist with their projects. This service is free for the design teams across Australia and New Zealand. We also strongly recommend to have the monitoring systems either integrated or retrofitted to the seismic devices, or for that matter, the normal bearings and deck joints across Australia and New Zealand. Why? Because it would provide us a healthy footprint or fingerprint of the structure once it's installed. And when something goes wrong, it will be very easy to identify what's going wrong in which section of the product or the structure, that way avoiding costly comprehensive inspection of the structures. Providing the products and designs is also complemented by Mageba's capability to also install these products on the site. So whether it's bearing deck joints or seismic devices like lead rubber bearings, pendulum isolators, shock absorbers, and whatnot, Mageba has capable network of subcontractors and in-house team of engineers to assist with those installation to be compliant with various codes and specifications. A quick snapshot of what solutions or products Mageba offers to the market. So Reston pendulum. So this is a curved surface slider that behaves as if a pendulum is moving under the seismic conditions, and it helps the structure to come back to its more or less original position after the seismic event has occurred. It comes into either single curved surface slider, double curved surface slider, or triple curved surface slider. Lasto LRB, so lead rubber bearing, and the high damping rubber bearing. So these are the customized or improvised version of the normal laminated elastomeric bearings, whereas either the lead core or specially compounded rubber, a harder rubber, dissipates the earthquake energy and avoids the damage to the structure. Seismic isolation solutions apart from the bearings, which are the shock absorbers, shock transmission units, and preloaded spring dampers. They have different internal construction mechanism. However, the principle that they work on is very much similar. And just as a quick analogy, they work similarly as the sash belts into our cars these days. The sash belts, as you know, that if you pull them slowly and steadily, they come off. But as soon as you get a jerk, they lock up and save you. So this is how the shock transmission units, shock absorbers, and preloaded spring dampers work. They are tuned to allow the very slow and steady service movements, whether it's thermal or braking. But the moment it encounters a seismic, a jerk from a seismic event, they lock up and then transfer the load from the intended structural member to an intended structural member rather than damaging the entire structure. Some of the monitoring solutions, we either have the permanent monitoring solution, which can be integrated as part of the seismic isolators, bridge bearings, and deck joints, or we can have retrofit temporary or so-called portable monitoring devices, which we can carry with us on to each to monitor the loads, movements, and rotations as and when required. Some of the project references where we have been successfully using our solutions and helping engineers to solve the problems. ANZ Triangle Center project in Christchurch, where we supplied curved surface sliders to solve or to make this building completely isolated from the earthquake events. Sydney Opera House, the stage of the Sydney Opera House, as we all may be aware, it rotates to create the different scenery effect into the dramas and plays that are played. This stage is then supported by the Magiba solution, which is a bearing capable of taking seismic and non-seismic loads and movements. Bunbury Outer Ring Road, Old Mangere Bridge, all these bridges have been equipped with the bearings and expansion joints that are locally designed. Some of these products are also locally made in Australia, and some of them have been made in Magiba's Shanghai factory in China. Seismic isolation reference project in particular, we have the oil refinery, we have the commercial industrial buildings of any sort that will need to be seismic seismic isolation incorporated into its design to save the damage to the property and the people. With this, I would like to thank all of you and invite you to call us if we need any design assistance. Visit our LinkedIn page to find out the references. We provide this free design assistance service to the bridge designers, building designers, architects, and specifiers to assist with their problems related to whether it's movement, normal movement, or seismic movements. Thank you very much.
Thanks, Brandra. Well, now it's our audience's turn to get involved. So please submit your questions in the chat box and let me know who you would like your question directed to. Also, don't forget to pop your name in so I know who's asked the question. Now, a big thank you to everyone who did submit a question while registering for today's webinar. So what I might do is I will actually start my first question to you, Masood. And this question's come through from Robert. And his question was, is there a current system to minimize the impact of seismic activity for the buildings?
Yeah, sure. There is plenty of different devices as per what Virendra was explaining about the dampers and base isolation. All of these kind of devices can minimize the impact of earthquake on both building and bridge. However, the most important one that can minimize and provide functionality as well is seismic isolators. And what kind of isolator is highly depends on the behavior and specification of superstructure that we are designing for.
Awesome. Thanks so much, Masood. Hi, Virendra. Yes, we can see you now. Great to have you. I will jump in. We've got a few questions which have come through live. So I might jump into one of those. And that one was from David. So big hello to David who is watching today. Now, David has a question for you, Masood. Can you please explain? I also think he said great presentation, Masood, by the way. Can you
Thank
please
you.
explain how the lead core energy absorption contribution is designed? Did you ever have a situation where the system is supercritically damped?
Actually, the point is that for designing lead rubber bearings, it's a kind of iterative process. And what I mean by that is that we normally get initial data from the engineer, including the vertical loads as well as the seismic specification of the site. And based on those data, we make a guess in terms of, not necessarily a guess, actually, we consider the acceleration spectrum of the site, actually, and we consider a target in terms of the required period as well as the displacement. Based on those data, we go for a preliminary design of the system, the size of isolators, the lateral stiffness, and the required damping to drag down the displacement after earthquake. And in terms of the second question, no, the point is that we normally, after the initial designing, we go for proportioning or optimizing the system. And what I mean by that is that we try to make a kind of proportioning between the size of isolators, the required stiffness, as well as the displacement. And when it's getting done, we pass all of the outcomes, including the effective damping, effective stiffness, to the engineers with the written parameters. We normally tabulate that to be quite easy for engineers, and they can put the data in their software, go for some analyzing, and again, give us back the axial loads, their reaction that they've got from the structure, and we go for a few times trying and error until we end up to a reasonable answer for the system.
Awesome, thank you. We had another question come through live, and this one was, can the old structures be retrofitted with LRBs, or has it to be does it have to be planned for a new structure only?
Oh, very good question, actually. It's a $1 million question. The joy of designing by base isolation is that you don't necessarily need them for new project. You can use isolators for any kind of project at any stage, actually. And we already have got many projects, particularly in Turkey and in other seismic area like China and Japan, that even after a few years from using the project, the client or engineers have noticed that the traditional system hasn't been good enough in terms of providing the required performance. So they have decided to use base isolation for an existing project. And the process is quite easy. And the most important one is that among all other options for strengthening or retrofitting a project, base isolation is the most effective and the most financial viable option. And if I just gonna quickly explain how it works, is that we normally prepare or design some temporary work for existing project, cut the column or any piece of existing structure that is required, put the isolators in place, add some grout on top and bottom of that, release the pressure that already have provided with some viscose jacks or whatever. And after that, the project would be ready to go. And the point is that at the moment in different countries, including New Zealand, China, base isolation is getting implemented for those projects that probably have less for many, a few 100 years ago. It's a historical project. And I exactly recall that the other day I was in Italy for one of those conferences, as I was talking with one of researchers, designers of base isolator, and I told him that I really enjoy when I see Italians are using base isolator, for example, for a 300 years old project. And he smiled me and said that the age of projects they are putting on base isolation is considerably more. They do have probably projects with 500 years old or something that are getting base isolated.
Awesome. So interesting. Virendra, I'm going to bring you into the conversation. So we had a question come through from Alexander. And the question was, how are modern bridge designs in Australia adapting to improve seismic resilience, especially given that we're not traditionally seen as a high-risk earthquake region?
Correct, exactly right. And this is a spot on question. Unfortunately, the answer to this is the modern bridge designs in Australia are actually not adapting to the seismic resilience consideration into their design. And this is why this is the very purpose of this webinar to educate and increase the awareness amongst the structural and bridge engineer fraternity. The seismic resilience consideration is also quite important for the structures like bridges, hospitals, stadiums, hotels, and any other structures that are of public significance. Uh, it is quite easy to adapt it. However, it needs specialized inputs from someone like Masood, who's designing the seismic devices and seismic solutions for half decade now. So we invite all the structural and bridge engineers to contact us when they're designing their next project so that we can more efficiently and optimally include the seismic resilience consideration into their designs.
Awesome. Thank you. We've had a few more live questions come through. So the next one's from Andrew in Queensland. Hi, Andrew. His question is, what is the difference between a pendulum bearing to a pot bearing? And can you use a pendulum bearing for a skewed bridge or structure?
The point is that pendulums are considered as an independent system that can rotate or move during seismic actions. And if we use them for a bridge actually, you consider, for example, some extra loads on that one as well, like brake load or wind load or whatever. The pot bearings is a little bit different. The pot bearing normally are fixed. We use pot bearings for buildings in combination with lead rubber bearings. The point is that pot bearings are flat. However, spherical bearings do have a concave part that can provide a rotation and as well as recentering capacity as well. Pot bearings cannot use separately because they are not capable of providing recentering force. That's why we use them to be combined with elastomeric bearings. However, the advantage of pot bearing is that they effective damping is more than any other devices. So by combining lead rubber bearings and pot sliders, you can provide a soft enough system as well as high level of damping. However, for spherical bearings, you can provide the rotation and recentering force independently, and you don't need to use any other device in combination.
Well, Masood, while I have you, probably the next question which has come through is, what is the effect of the ground soil in the selection of the base isolation?
The point is that it's going to affect the design of the system, not necessarily the kind of device. The point is that for soft soils, the acceleration spectrum normally going to be higher than the strong soils or stiff soils actually. And the kind of analyze that you consider for soft soils would be different as well. We normally recommend for nonlinear time history analysis when you are dealing with soft soil. And normally the demand that you end up, particularly for displacement and period for soft soils would be more than other categories of soils. However, it doesn't necessarily gonna make any difference in terms of the kind of device that you're going to go for. We normally choose the device or type of device based on the specification of building or bridge or superstructure rather than the soil type.
Excellent, thank you. We had
No worries.
another question which came in. I think there are a few for you here, Masood. And the one
Yeah,
is,
sure.
are these lead rubber bearings the same as standard elastomeric bearings that we use on bridges? If not, what are the advantages of using these over the other?
Very good question again. The point is that the traditional elasto bearing that we use for bridges normally are made with low damping and low shear strain capacity. They are made with quite hard and a low shear capacity actually, which can provide just a minimum lateral displacement capacity for us. The natural rubber bearings that we are using to manufacture LRBs are a little bit different. And the minimum shear strain or elongation that we normally consider for this kind of isolators would be up to 600%. I mean that we normally run a kind of testing called as elongation that put a piece of rubber under tension and it's going to be stretched up to fracture and it cannot be less than 600%. So by using LRB, we normally end up to a shear strain more than 200%. By conventional elastomeric bearings, you're normally going to end up to quite less lateral shear capacity.
Awesome. We've had a question come in, Virendra, with regards to the Australian or the current Australian standards, for example, AS 5100, around addressing seismic loading in bridge design. And are there plans to evolve these provisions?
Definitely. So AS5100 Part 2 does provide a guidance on to what considerations needs to be included while calculating the loadings for the bridges, including earthquake loading. However, I acknowledge that it is not sufficient in terms of full seismic resilience consideration. And on behalf of the Australian Standard Code Committee, I assure you that there is work in progress to include more guidance or more detailed prescriptive guidance as to how we include seismic resilience to the extent that it is required. It will be in near future. The next revision would definitely include those provisions.
Thank you.
Sorry, may I add something here?
Yes, please.
The point in terms of the Australian guideline is that, particularly for what I noticed from 1170 commentary, was that for building, it mentions that non-structural elements even in Australia needs to be designed for floor acceleration. And we know that floor acceleration going to escalate along with the height of building. So by using base isolator, you're going to minimize the floor acceleration and it's going to end up some saving to design non-structural damage. And if I'm going to bring up a sample, I would refer to a data center in Auckland, New Zealand. And base isolator ended up to huge saving in terms of non-structural elements because even though Auckland is not as seismic as, for example, South Island, and probably its seismicity would be quite similar to Australia, by decreasing the acceleration of flow, they could save plenty of steel elements that they needed to fix non-structural elements, including piping, lighting, blah, blah, blah. And this is something similar for bridge as well. For bridge, we are using structural bearings at the moment. So in terms of cost, a structural bearing would be quite similar to a seismic isolator. However, in terms of performance, it would be quite different. I mean that one of issues that we do have with bridge over here in Australia is about the tension or uplift. And the point is that because structural bearings are quite stiff and strong, it's going to it work like a rigid element, and it's going to transfer the tension load or uplift to the deck and to the pier as well. However, by using base isolation, because we are softening the system, it's going to minimize the stiffness, and so less shear basing, less shear base force actually going to be transferred to pier. So less force on the pier abutment and less structural elements you're going to use for the pier as well. So in somehow rule of thumb, by using seismic isolation, not only you are improving the performance, but also probably you're going to end up to some saving as well.
Awesome, thank you.
No
And hopefully that's answered one of the other questions that we came in. So thank you for that. I appreciate that.
No worries.
We've got a question which was, how frequently would a bridge with LRBs require maintenance when compared to bridges without them? Is it cost beneficial in the long term, even with only medium seismic activity, which I think you've addressed in that last answer, but how frequently would you do they require the maintenance?
We highly recommend to use a health monitoring system for base isolated bridge actually, and we don't normally recommend inspection because of using base isolation unless a major earthquake has happened. By using health monitoring system, you can collect all the required data over time and make sure that the bridge or your project is sound and safe. But in general, we don't need any kind of visual inspection, turning up on the site just to inspect the isolators. Definitely, if an earthquake happens, you do need to turn up over there, making sure that visually and generally the isolators work.
Awesome, thank you. Look, I
No
think
worries.
we're actually pretty much gone through most of our questions. So I was really wondering if we could potentially, if I could pose to the two of you, like as engineers, what would you both say are the key takeaway messages that you would like to leave with your audience today, or the main points, I suppose, of your presentation? So I'm not quite sure who wants to go first. Maybe you, Virendra?
Virendra, yeah.
Yep, definitely. Thanks, Megan. Thanks, Masood. Look, definitely the key purpose of this webinar is to increase the awareness and educate the structural engineers that seismic resilience incorporation into their designs is quite critical, as we're experiencing a lot more frequent earthquakes across the globe, also to the places where it has never happened. It is not that difficult, and it is not as costly as one would have thought. I think the best way to get started is just to give us or any other seismic experts a quick call for a quick chat about their current projects and how they can incorporate the seismic resilience considerations into their designs in the early stages, so that the space proofing, the constructability, the manufacturability, the testing requirements, performance requirements, all can be pre-discussed and preempted, so that there is no hiccups during the post-tender and construction phases. We welcome all inquiries, all phone calls, all emails related to these. Me, Masood, and our entire design team in Mageba, Australia, and Mageba globally will be gladly assisting all those inquiries.
Awesome, wonderful. And Masood, your final comments to our audience today.
Sure. Thank you very much. Our main message to Engineers Australia is that if we are designing or building a project, that it needs to be functional constantly, and we cannot consider any kind of downtime, as well as if the project is or covers some elements or any kind of equipment that's going to be sensitive to acceleration, we do need to think about using seismic isolation systems actually. And the point is that even though in Australia, although it's not as seismic as some countries like New Zealand, we still do have some potential of earthquake. So for hospitals, for structures like hospitals, data center, and infrastructures like bridges, we highly recommend to consider seismic isolation. Thank you very much.
Well, look, that's all the time that we have for today. So please join me in once again thanking Masood Pomasood and Virendra Godke for their time and input. I'd also like to thank Engineers Australia's industry partner, Magiba, for their support today. Now, we would appreciate if you could take a moment to complete the short feedback form, which is included in the description box below. Your input really does help us to improve and plan future sessions for you. Thank you again for joining us today, and we do look forward to seeing you at our next Industry Partners event. Good afternoon.